Hello, everyone. Today, we're going to discuss the two-sum solution. Now, if you haven't watched the previous video, we discussed the brute force method, and that is time complexity n squared, because we're going to iterate through each element of the list. And for each element of the list, we're going to iterate through each other element of the list. So essentially, it's going to be two nested for loops. I definitely recommend watching that beforehand just to see the brute force approach. It's a little bit simpler. This approach is also simple. We're just going to change up the problem just a little bit. So let's go ahead and read it. So the two-sum problem is given an array of integers or vector of integers, essentially a list of numbers, numerics. What we're going to do is we want to be able to sum up two of those elements to make up a target. So for example, like if we were given this list of numerics, so 2, 7, 11, 15, we want to be able to add two of these elements to get to this target of 9. So we could see clearly that 2 plus 7 will give us the target of 9. Now, as the result, what this problem is expecting is for you to return a vector with those two indices. So once again, going back to this problem, 2 plus 7 is equal to 9. So the 2 has a corresponding index of 0 because it's the first element, and the 7 has a corresponding index of 1 because it's the second element. So that's really what we're looking for. Now, this approach only really works when the linear approach only really works when the solution is already ordered. If the solution is not already ordered, then you're going to have a bit of a headache kind of ordering it first and then finding the elements that do make up your target, kind of tracing back to the original vector to find what were their original positions were. There's a lot of edge cases. So I don't really recommend this unless the vector that you're given is already ordered. So that's one thing to keep in mind whenever you interview. Always make sure to ask for conditions. Make sure that you really understand what the problem is asking you, and specify certain criteria, because if you're given an ordered list, it's going to be a much different answer than if you're given an unordered list. So once again, we're only considering this scenario where it's ordered. We're not, please disregard these two at the bottom. Now, what's the approach that we want to take? So let's say, for example, I have these values. I'm just going to write them out here. I have 2, 7, 11, and 15, and I have a target of 9. Target of 9. So ideally, what we want to do is we want to use what are called pointers. They're not really pointers. In C++, pointers actually mean something else. It's a memory address. But what they are is they're going to be references, or they're going to be indices, essentially, index. And we're going to have one for the left pointer and one for the right pointer. Now, another way of saying that, so left pointer is just going to refer to the first index. That's really all it means. So it's going to start off at index 0. And then the right pointer is just going to start at the end of the last index, which is always going to be the size of our container minus 1, right? So that's really what we're going to do. And then once we know that, we're going to have the first element, the last element. We want to add them up together and see what we have currently. So this is going to be our current sum, 2 plus 15. That's going to be 17. And we're going to compare that to our target. We're going to see, did we reach our goal? Can we return these two indices? And we can see that, since 17 and 9 are not equivalent, we can't do that. Now, what's the next step from here? Well, the next step from here is we have to compare, well, is 17 bigger or is it smaller than 9? Because we know it's not equal to 9, but is it bigger or smaller? In this case, we can see it's bigger. So we want to be able to reduce it. We want to be able to shrink it down. So what makes more sense in terms of bringing down the value? We know that these are sorted in ascending order. So would it make more sense if I were to, instead of using this 2, use the 7, essentially increment the left pointer? No, right, because that's going to increase the sum by 5. Notice it's increasing the value as I shift my left pointer to the right. Instead, if I want to decrease the value, what I'm going to do is I'm going to decrement the right pointer, which is starting at 15, and I'm going to go ahead and push it down or decrement it down to 1 index lower, and that's going to give us the 11. So actually notice it's going to get 4 smaller, and that's going to get us closer to the target. And we're going to have this kind of balancing act of going through each iteration and deciding, is it the right size? If it's the right size, we're good. We found our answer. We can return the corresponding indices. If not, we have to compare. If it's bigger, then what we want to do is we want to decrement the right pointer. And if it's smaller, we want to increment the left pointer. Right, so that's pretty much the solution there. Let's see it on paper now. So here I have 2 plus 15. That's too big. So what we're going to do is we're going to decrement the right pointer to make it 11. And now 2 plus 11 is 13. It's still too big, right? So what do we want to do? We want to bring this down to 7. So now it's going to be 2 plus 7. We're going to go ahead and add those up. That gives us 9. And that is our answer. So there we go. We found our answer. And we can go ahead and return those indices. That's going to be the approach on paper. Please make sure that you feel comfortable and understand kind of the logical approach, because if you can't do it on paper, it's really difficult to do it, to actually implement it in terms of coding. So for this, let's get started and let's start coding it out. So I'm just going to go ahead and copy and paste it into my online compiler. I've even written a test case here that shows that same example from earlier, just so that we can test it out. It's not gonna work for all cases on Leet code because they don't order it by default. You may notice that I need to include my vector library, something I forgot, but I also previously was working with my algorithm, and this is so that you have access to your sort function. I'm not using it in this case because I'm assuming it's going to be already sorted. I'm assuming that this vector nums is going to be sorted, so I don't have to worry about using that sort function. All right, so let's go ahead and get started. So I want to have a place to store my results. Let's go ahead and have that set up as our vector of int, which is going to be called found indices. And this is where we're going to find, what those two indices are for the elements that add up to my target. The next thing that I want to do is I want to go ahead and set up those left and right pointers. So we know that our left pointer is going to start at index 0, right? So because the first index of any container is always going to be 0. And then my right pointer is going to be the size of my container minus 1. So there we go. We've established our left and right pointers. And why we have to also consider, when is this valid? Like when should we stop? At what point have we exhausted all the possible combinations? And at what point are we not repeating ourselves? Or are we actually having unique values that we can come up with answers? And that's really when the left pointer and the right pointer are not on top of each other. If they come in contact with each other, if we get to a point where, let's say, for example, it might be a little bit easier to see here. Let's say I'm going to put a left here and a right here. Let's say I decrement this to the right. I decrement this once again to the right. And then I get to a point where I have to decrement the right once more. So let's just have it here. And now they're sitting right on top of each other. Well, the problem says that you may not use the same element twice. So in this case, because I'm comparing the two same indices, this is no longer valid. So you'll notice that whenever they overlap, it's invalid. So when is it valid? It's whenever the left pointer is less than the right pointer. It's whenever the left pointer is to the left of the right pointer. So whenever it has that ordering, it's valid, and we can still keep iterating through the list. So that's why our condition will say, when the left pointer is less than the right pointer, these are valid possibilities. That's one way to think about it. Now, what do we want to do here? What we want to do is we want to find out what the current sum is. Before we did 2 plus 15 to get that 17 starting value. So what is our current sum? Well, it's going to be the first value plus the second value. So let's also define the first value and the second value. So the first value is going to be nums at the index left pointer. And here I'm just being a little bit more verbose, but it's very important to have maintainable code that you understand. You don't want to write code that's kind of harder for someone else to read. So always try to make it as simple as possible. So here we have our right pointer. And these are the elements that we have, the 2 plus 15 in that example, right? So 2 plus 15. We're going to go ahead and set up our current sum. So our current sum is really just the first value plus the second value. Or I could have called it the left value and the right value. That might have been a little bit more appropriate. Let's just go ahead and make that change to make it a little bit more clear. There we go, the left value and the right value. Okay, perfect. Now, what we want to do is we want to compare it. We want to find, did we reach the target? Did we get kind of the success that we were looking for? So is our current sum equal to the target? If so, we know that we found the indices that we were looking for. We can go ahead and just push them back to our vector. So let's push back the left pointer. And let's push back the right pointer. Now remember, we're pushing back the indices, which are the pointers. We're not pushing back the elements, that were added up together, because that's what the problem was asking. So that's the case when we find them. If that's the case, then there's no more reason to search. We can just go ahead and break out. But there's those two other conditions. What if it's too big? As we saw before, if I did 2 plus 15, that's 17. That's larger than my target. So else if my current sum is greater than my target, then what I really want to do is I want to make my sum smaller. And in order to make the sum smaller, I want to decrement my right pointer. I want to make it go downward here. So what we're going to do is we're going to go ahead and get the right pointer and decrement it. And what if it's on the other hand, my current sum is smaller than my target, right? So in that case, I want to make my current sum bigger. So then I would get my left pointer and increment it. And that's what the else is referring to. So I'll get my left pointer and increment it. And once again, this is just to put a little bit of comments here, this is just to make our current sum smaller. And then this is to make our current sum bigger. Our current sum bigger. Okay, there we go. And once this loop is complete, we know that there's exactly one solution. So it should be, so our found indices should be populated with the two indices of the elements that add up to the target. So all we need to do is return our found indices, and that's it. That's pretty much our solution. Let's go ahead and run it through our test case. Hope I didn't make any syntax errors. Oh, looks like I did. Right pointer. Oh, there it is. So here's right pointer. Looks like I forgot to type the ER. Okay, so that's 0, 1. And here we can see that those are the two values that we want. 2, which is 2, which has the index of 0, and 7, which has the index of 1. If I add those two up together, I'm going to get my target. And so this is this has a time complexity of linear, just because if it's already sorted, I only need to go through this list, all the values in the list one time. So let's say if this has 100 elements inside of it, at most I'm going to perform 100 searches in that case. So I hope that makes sense. I did kind of have to modify the problem a little bit just to get it to fit this scenario. Otherwise, I tried to do it in the current Leet code and it ran into some edge cases that were a little bit funny. So I hope you enjoyed. Thank you so much for watching. Please like, share, and subscribe if you did, and come join us for more content on solving Leet code questions. Thank you.